All right, here's our second video regarding concavity, but we'll take it all the way back to the first derivative as well, and we'll move from there. Let's start with the function f of x. Let's start with a better marker. F of x equals x to the fourth minus 4x cubed plus 10. What we want to do here is analyze this as completely as possible with the tools that we have amassed thus far and try to draw a good graph, an accurate graph. Well, as I've mentioned before, we have tools that predate our calculus learning. We know, for example, that this has a y-intercept, the point 0, 10. We also know that this is a quartic, a fourth degree polynomial with a positive lead coefficient. You should be able to visualize what could happen to the graph of a fourth degree polynomial. That you would be looking, now it might not be exactly symmetric across the y-axis, but you'd be looking at something like a W. Whereas if the lead coefficient were negative, you would expect to see something more like an M. It may not look exactly like that. The two sides might not be symmetric, but something like that is going to occur. Now, so we have an intercept. There are x-intercepts as well in all probability, but those are more difficult to find. The y-intercept, easy, 0, 10. The domain is all real numbers, so there can't be any vertical asymptotes. Let's start then with our first derivative. F prime of x equals 4x cubed minus 12x squared. Let's factor that completely. We can pull out 4x squared. That's x minus 3. And what we have is two critical numbers, 0 and 3, when we set this equal to 0. So, let's draw a number line representing the domain of the function. Our critical numbers, 0 and 3. Let's test our intervals. If x is negative, let's just say negative 10. X squared is always going to be positive. Negative 10 minus 3 is negative. The function is decreasing here. Between 0 and 3, let's try 1. Positive times negative. Decreasing still. Note, the sign of the first derivative did not change around this critical number. Greater than 3, let's try 10. Positive, positive. So, since the function is continuous throughout here, across 0, we will consider this as one interval. The function is decreasing from negative infinity to 3 and increasing from 3 to infinity, which means that we have a local minimum. That local minimum occurs at x equals 3. At x equals 3, we would have 81 minus 108, negative 27 plus 10, negative 17. All right, that's what we can get out of the first derivative. So, let's go to the second derivative. Going back to the polynomial form here, the second derivative, f double prime of x, is 12x squared minus 24x. We will do with this exactly what we did with the first derivative. So we'll factor out 12x, and we are left with 12x times x minus 2. If we set that equal to 0, now we don't call these critical numbers. They are simply zeros of the second derivative. Again, we draw a number line representing our domain. The zeros are 0 and 2. We test the intervals for the second derivative exactly as we did for the first. We try a number less than 0. Try negative 10. Negative times negative, positive. Try 1, positive times negative, negative. Try 10, positive times positive. Now, these plus and minuses, these are not telling us increase and decrease. They are telling us concavity. The function is concave up from negative infinity to 0 and from 2 to infinity. The function is concave down where the second derivative is negative, from 0 to 2. We have 2 places on the graph. Now this is a polynomial. It is differentiable everywhere, so the derivative does exist at these 2 points. You could draw tangent lines, and the concavity changes, so we have 2 points of inflection. I'll just label them inflection points. And our inflection points, well, when x is 0, we already know that's our y-intercept, 10. So the point 0, 10. When x is 2, we go back to the function. We're finding y. We're not finding a derivative here. We're finding the actual point on the graph. 16 minus 32, negative 16 plus 10 is negative 6. So those are our 2 points of inflection. So let's put this all together and draw a graph with greater accuracy than we have been able to attain previously, because we have an additional tool now. That's what we're doing. We're filling a toolbox with analytical tools for taking this function apart and figuring out exactly what is going on. All right, we have some pretty big values there, negative 17, 10. So let's scale our graph accordingly. Let's make this 5. Our x-intercepts and such, well, that's not a problem. We'll just keep these 1 each. Okay, now let's just look at the data we have. We know that we have a local minimum. When x is 3, y is negative 17, about there. We have 2 points of inflection, one of which is also a y-intercept. 0, 10, 2, negative 6. It is always helpful to plot other points in between ones that we know or beyond, to interpolate or extrapolate. Well, at negative 1, what we have is y is 15. When x is negative 1, y is 15. When x is negative 2, y is, well, it looks like it's about 58. So we can see that this function is decreasing rapidly down to here. When x is 1, y is 7. Okay. When x is 4. When x is 4, x to the 4th will equal 4x cubed. So when x is 4, y will be 10. Those points are helpful for a couple of reasons. Number one, knowing that the function is positive when x equals 1 and negative when x equals 2. Tells us by the intermediate value theorem that we have an x-intercept between x equals 1 and x equals 2. Knowing that the function is negative here and positive there says there's an x-intercept between 3 and 4. Now let's follow the pattern of what we have drawn here. From negative infinity to 0, the function is decreasing, we can see there, and concave up. Decreasing and concave up. Right? Concavity is up even though the function is trending down. From 0 to 2, the function is decreasing and concave down. So now the curvature changes. And we have an x-intercept between 1 and 2. From 2 to 3, the function is still decreasing, but it is now concave up. And then, from 3 to infinity, the function is increasing and concave up. And we know that we have an x-intercept between 3 and 4. Now, it doesn't look exactly like a W, obviously, but it does have that general shape wherein we're going to infinity as x approaches negative infinity, we're going to infinity as x approaches infinity. We can see also that this local minimum is also the absolute minimum of the function. The function never decreases again. And that's it.